Alise.
I'm Nick.
And I'm Ariana.
And I'm Katie.
Of this lab is to be able to calculate the experimental heat content of the candle wax.
The materials that we will be using are candles, a pencil, soda can, ring stand, aluminum foil, matches, water, thermometer, 100 milliliter graduated cylinder, aprons and goggles, and a water bottle.
First step is to weigh the sheet of aluminum foil with the candle. Right, 17.750. Alright, and then you would put it under the ring stand. And then
Next, you're going to want to fill a graduated cylinder with 100 grams DI water. And then put the DI water into the can. And then you're gonna take the can. Oh, and then you're gonna measure the temperature of the water. Make sure it does not touch the bottom.
That's about 20. Still going on. Alright, 21 and a half.
Okay, about 21 and a half degrees Celsius.
And you want to record that too.
Then we're gonna take the can full of water and then put it over right on top of the candle. Then we're gonna take the matches. We're gonna light a match. And light the candle. And take it off and measure the temperature. And then record the temperature of the water.
You would weigh the candle after it's burning.
Add 15.0.
Okay. 17.501.
Until the temperature remains.
Okay. Alright. That's the last.
Here are the calculations for the heat content of combustion of paraffin wax. So here's our recorded data, and we basically plugged in 100 milliliters for the amount of water used, 4.184 joules per gram Celsius, which is the constant, and 47 degrees Celsius, which was the temperature change, final 68 degrees Celsius minus initial 21 degrees Celsius. Then we concluded that 19,664.8 joules were derived, which can be converted to this amount of kilojoules. Thus, the 0.65 grams of C25H52, which was calculated by subtracting the final amount minus the initial amount of massive candle wax and the aluminum foil, and then converted it to moles by timesing it by its molar mass, which is for every 1 mole of C25H52, there are 353 grams. From there, we got the initial kilojoules that we found and divided it by the derived amount of moles of C25H52, and we were given our kilojoules per mole of C25H52. From there, we found our percent error by subtracting this experimental value minus the theoretical value, which is 14,800 kilojoules per mole. And our percent error was 27.8% error because we found a decreased value. One possible source of error that could have contributed to the percent error was the flame and the open system. The flame was on top of the candle, but it was also exposed to air, which could have caused flickering. Thus, the flame would have not transferred all of its heat to the can, thus the water, and the candle would have still burned, and that mass would have been accounted for, while the water would have not received all the heat, thus the temperature would have not rise as much. The observed temperature would thus be lower than required to because of the amount of candle that was being burned. And mathematically, the lower temperature, which would be the final temperature, derived would cause a lower temperature in the equation when deriving the Q of the H2O. Thus, a lower amount of kJ or kilojoules for every mole. Another source of air is the metal soda can use. The metal of the can could absorb some of the heat, not fully transferring all to the water, thus resulting in a lower temperature, thus a lower kilojoules per mole. Metal is a good thermal conductor, which could later release the absorbed, though a small amount, to the atmosphere and not the water directly. Therefore, as in the other example, the final temperature would have been lower than expected, and while the candle would have still continued to burn, therefore the mass would have increased.